There. Now we should be live.
Great. Yeah, yeah. Hey, anyone who's watching, thanks for watching. Yeah. Oh, this is interesting.
Um, the ambiguous language.
Yeah,
Let's see
yeah.
here.
It's a cool location.
All right, I guess I'll get started. So let's see. Ambiguous language. The drawing in figure 3.3.3 is a famous example of visual ambiguity. When you look at it for a while, you'll probably see either a silhouette of a young woman wearing a large hat or an elderly woman with a large nose. Whichever image first pops into your mind. I actually didn't see the old woman until they mentioned that, but I do see the nose.
Yeah, that's cool. Huh.
Let's see. Try to see how the drawing can be interpreted in the other way. Hint, the mouth of the older woman is the necklace of the young woman. Once most people see one of the images, it's difficult for them to perceive the other. So it is with ambiguous language. Once you interpreted the sentence at the beginning of this section in one way, it may have been hard for you to see that it could be understood in the other way. Perhaps you had difficulty even though the two possible meanings were explained. Just as many people have difficulty seeing the second interpretation from the drawing, even when they're told what to look for. Although statements written informally may be open to multiple interpretations, we cannot determine the truth or falsity without interpreting them one way or the other. Therefore, we have to use context to try to ascertain their meaning as best we can. Okay.
Yeah, yeah. And then I guess like the math language usually removes that ambiguity. So it's like a very precise meaning. Although I guess even sometimes math language could have ambiguity. Like if someone says for all x, you're assuming like you have to rely on the context to know like what domain you're talking about.
Right. You can add ambiguity into the math language.
Yeah,
And yeah, equally, I guess you can kind of take ambiguity out of the informal language too if you're just a little bit more thorough at your language usage.
yeah,
Hmm.
yeah, definitely. Yeah, like in that statement below, they say for all x and d. So I guess they're specifying the d there, but they could have just said for all x, and then it would be ambiguous. But you could understand what d is from the context.
Yeah. Well,
Yeah,
it's you want this section?
yeah. So negations of multiply quantified statements. You can use the same rules to negate multiply quantified statements that you use to negate simpler quantified statements. Recall that it is not the case that for all x and d, p of x is equivalent to there exists an x and d such that not p of x, and it is not the case that there exists an x and d such that p of x is equivalent to for all x and d and not p of x. We apply these laws to find the negation of for all x and d there exists a y and e such that p of x y by moving in stages from left to right along the sentence. First version of negation. So firstly, we're negating for all statements. So that's going to become like everything has this property. The negation is going to be there is something that doesn't have the property. So there exists an x and d such that not there exists a y and e such that p of x y. And so now we have the negation of the final version of negation, the negation of an existential. And the negation of an existential is going to be a for all statement. Like it is not the case that there's something that has the property is equivalent to everything doesn't have the property. So we have there exists an x and d such that for all y and e, not p of x, y. So we kind of proceeded step by step to find the negation of a statement that has a for all and a there exists. Um, and I guess intuitively, like the original state, like the for all x and d, there exists a y and e such that p of x, y is saying like for each of the things in d, there's something corresponding to them that has this property in relation to them. Like like for example, every integer has an additive inverse. It's something that you can add to it to get to 0. And then if you want to negate that, then you want it to, like, it's not the case that everything in there has everything in D has something in E such that the P relation holds between them. Then you want there to be something in D such that the P relation doesn't hold between it and anything in E. For everything in E, the P relation doesn't hold between that X and it. But yeah, we kind of applied those negation rules step by step. And then we can do it again for the next one, where you have a there exists followed by a for all. So similarly, to find it is not the case that there exists a x and d such that for all y and e, p of x, y, we have, so the first step, we're negating an existential, so we're going to have for all x and d not for all y and e, p of x, y. And then next part, we're negating a for all statement, so we're going to have an existential followed by a negation. For all x and d, there exists a y and e such that not p of x, y. Yeah. And then these facts can be summarized as follows. Oh, yeah, and actually, even like there's like a kind of nice pattern to them. Like if you're negating, oh yeah, and then it comes up in the box. Like not for all x and d there exists a y and e such that p of x, y is equivalent to there exists an x and d such that for all y and e not p of x, y. Not there exists an x and d such that for all y and e, p of x, y is equivalent to for all x and d there exists a y and e such that not p of x, y. So kind of like the like algorithm, or like just like the just the sort of rule to it. Like we saw earlier, like the reason behind it, but kind of the pattern is that if you're negating a statement with two quantifier with a for all and then a there exists, or vice versa, you just reverse the order of the for all and the there exists, and then negate the thing after those. So like in the first one, we had for all followed by there exists. So in the negation, we just reverse the there exists and the for all, so that there exists comes first and the for all comes second, and then we negate the thing that comes after them. Yeah.
Okay. So far, that seems easy enough. So let's see. Now, what did you call these different parts of the formula? You have the quantifier, and then you have the the predicate, right? Or the scope?
Yeah, the predicate. Yeah, and the predicate is the like within the scope of the second quantifier. Or I guess like the scope of the for all is like the scope of the for all x and d includes all of it, but then the scope of the second, or the scope of the first quantifier includes the whole thing, but the scope of the second quantifier includes just the stuff that comes after that quantifier.
Okay.
Yeah, so I guess you're negating like the thing that's in the scope of the second quantifier.
It seems like the algorithm has always been, if you have a quantifier, whether it's for all or there exists and its scope, you'll change the quantifier to the other quantifier, and you'll negate this scope. So like if you had for all x and then p of x in the quantifier, and you negated it, you would end up with there exists an x such that not p of x, right?
Yeah, yeah, exactly. And then here, I guess we're kind of doing like a generalized version of that, because in each of these cases, we're also changing the quantifiers and putting a negation in the scope.
Exactly. And the scope just
Yeah,
happens to include another quantifier. So you just recursively do the same application negation to it, right?
yeah,
Okay. So like if we have for all x, and then in the scope we have for some y, and then like p of xy, and we wanted to negate it, then we would turn the for all into a for some x and negate its scope, which would look like uh, this. And when we negate its scope, we're negating a quantifier, so we can simplify it further.
yeah,
So we would change that quantifier to the other kind and then negate its scope. I believe it'd be like that, right?
yeah, 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 exactly.
Okay. So I think
Yeah,
that algorithm is probably the heart of the entire chapter, but we'll see.
yeah, yeah, it's really cool. Yeah, definitely bringing a lot of concepts together.
Yeah. Let's see. Negating statements in the Tarski world. Refer to the Tarski world the figure 3.3.1, which is reprinted here for reference. Write a negation for each of the following statements and determine which is true, the given statement or its negation. Okay, so for all squares, there exists a circle y such that x and y have the same color. Something like this. So the negation of all that would be there exists an x such that, or there exists a square x such that for all circles y, it's not the case that the square x and the circles y have the same color.
Yeah.
Let me just reread that.
And then to capture that there are square and circle, you can also say like there exists an x in S and there exists a y in C.
True. Guess I'll put that on the next one.
Yeah. Yeah, and then the question is that true?
So first off is the given statement, which was for all squares x, there exists a circle y such that x and y have the same color. Okay. So for all squares x, here's a square. All the squares would be here and here. A circle y such that they have the same color. Actually, I don't see a circle that matches this black square.
Yeah.
Now, let me make sure I got the negation correct. Intuitively, so it's saying that for all squares, there is at least one circle with the same color. So we want to say that there's some square, okay, such that there's no circles with the same color. And that's the
Yeah.
one.
Yeah.
I wonder if the given statement and its negation, they always have the exact they're always the exact opposite cases, right? There's no case in which in which they're both true or both false.
I guess. Let's see. Um, let's see. Oh, oh, oh yeah. I guess because I guess the statement. If you have a statement and its negation, one of them has to be true. Yeah, and that's like always the case. Because like if one of them is false, like suppose that one of them is false, that means the negation is true. And suppose one of them is true, then the negation is false, because just by the rule of negation from propositional logic.
Hmm.
And each of them has to be either true or false. They can't be like neither true nor false. So yeah, by that fact, one of them has to be true, one has to be false.
Interesting. So let's see the next one. There is a triangle X such that for all squares Y, X is to the right of Y. So you can say there's a triangle X in, I suppose, T such that for all squares Y in S, X is to the right of Y, which means there's at least one triangle such that all of the squares are to the left of it.
Yeah.
And the negation will be for all triangles, there exists some square such that the triangle is not to the right of it. So all of our triangles, I guess first we can check if the original statement is true. So, well, let me identify all the triangles. Here's a triangle, here's one, that's all of them. So there exists some triangle such that for all squares, the triangle is to the right. Okay, well, if I'm reading that correctly, in any case, these triangles are not to the right of this square, nor this square. So none of the triangles are actually to the right of these squares. So the
Yeah.
negation is going to be true, which is for all triangles, there exists at least one square that's not to the left.
Yeah.
Yep, seems to be the case.
Yeah.
Okay, again, that's the negation. So let's see. Okay, looks like we were correct. Negation is true in both cases.
Yeah.
Let's see. You want this section?
Yeah. All right. Order of quantifiers. Consider the following two statements. For all people X, there exists a person Y such that X loves Y. There exists a person Y such that for all people X, X loves Y. Note that except the order of the quantifiers, these statements are identical. However, the first means that given any person, it is possible to find someone whom that person loves, whereas the second means that there is one amazing individual who is loved by all people. Reread the statements carefully to verify these interpretations. The two sentences illustrate an extremely important property about multiply quantified statements. Yeah, and on the next page, in a statement containing both for all and there exists, changing the order of the quantifiers usually changes the meaning of the statement. Interestingly, however, if one quantifier immediately follows another quantifier of the same type, then the order of quantifiers doesn't affect the meaning. Consider the commutative property of addition of real numbers, for example. For all real numbers x and for all real numbers y, x plus y equals y plus x. This means the same as for all real numbers y and for all real numbers x, x plus y equals y plus x. Thus, the property can be expressed more briefly as for all real numbers x and y, x plus y equals y plus x. Yeah, so the order matters if the quantifiers are different. The order can change the meaning of the statement.
Yeah, that makes sense. You could say for all cats and for all dogs. For all cats X and for all dogs Y, X and Y are mammals. You could say for some cat X and for some dog Y, X and Y love each other. And that would be the same as for some dog Y and for some cat X. Or for some dog X and for some cat Y, X and Y love each other. Actually, maybe that would be different. No, it would be the same.
Yeah. Yeah, I just mentioned them in a different order, but yeah, it's saying the same thing.
Let's see here. Quantifier order in a Tarski world. Look again at the Tarski world of figure 3.3.1. Do the following two statements have the same truth value? For every square x, there is a triangle y such that x and y have different colors. There exists a triangle y such that for every square x, x and y have different colors. So one is saying for every square, there exists a triangle y. Maybe I should. For every x in S, there exists a triangle y such that x and y have different colors. The other one is there exists a triangle y such that for every x, every square x, x and y have different colors. So one means that for every square, there's at least one triangle that doesn't match its color. The other one means that there exists one triangle such that it doesn't match the color of any squares.
Yeah.
Let's see. So my question is, I think obviously in a perfect world, these two have different truth values. um, in some particular Tarski world, maybe they would both be true. Let's see if that's possible though. For every square, there's a triangle such that X and Y have different colors. Well, if there was only two objects, a black square and a red triangle, then A would be true, right? Because for every square, there's at least one triangle with a different color.
Yeah.
It would also be true that there exists a triangle such that every square has a different color as well.
Yeah. 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 It would.
So, will we say that these two statements, like, they have different truth values? It seems like these statements structurally have different truth values, but in some cases would have the same truth value. How would you articulate that
Yeah.
distinction?
Yeah. Well, I guess there isn't like the structure. Yeah. So like you showed the structure. I guess doesn't guarantee they have different truth values. I guess it just means that like the statements, uh, they're neither equivalent nor contradict, nor do they contradict each
Oh,
other.
gotcha.
Yeah. Yeah. Because they can have different truth values, but they don't have to. So it
Okay.
depends on the particular Tarski world or their particular model, particular scenario where you're evaluating them.
Interesting. So I wonder, to show that two different statements have different, or how did you articulate it? Not that they don't have the same truth value, but
Yeah, so like they aren't logically equivalent.
right.
To be logically equivalent means they always have the same truth value in any scenario.
Ah,
Yeah, nor do they contradict each other. If they contradict each other, that would mean they always have different truth values.
right. Okay, yeah. Logical equivalence just means that they always have the same truth value in every scenario. So if there's a scenario that
Yeah,
you can think of in which they don't, then they're not logically equivalent.
yeah,
Okay.
yeah. But then I wonder, in the Tarski world,
Hmm.
their truth values be.
So for every square, there exists a triangle such that x, or such that for every square, there's a triangle such that the square and
Yeah,
the triangle have different colors. I think that that's true, and this one's false, which is that there's at least one triangle such that none of the squares have the same color as it.
yeah,
Because our triangles are here, here, and here. It's only triangles. And the gray triangles are out because there's a square that's gray. The black triangle is out because there's a square that's black. But we see that for every square, we have a square here, here, and here, and here. So at least one triangle with a different color. I think as long as there's two triangles with different colors, then um, every square is going to have that triangle with a different color because the square can only have one color.
yeah,
So yeah, like this black
yeah,
square is different from the gray one. Yeah, and the gray one is different from the black one. The blue one is different from the black one and the gray one as well.
yeah,
Let's see. And that's basically what they said.
yeah.
I'll read this next one. In some areas of computer science, logical statements are expressed in purely symbolic notation. The notation involves using predicates to describe all properties of variables and omitting the words such that and existential statements. when you try to figure out the meaning of a formal statement, however, it is helpful to think of the words such that to yourself each time they are appropriate. The formalism also depends on the following facts. Okay, let's see here. It says, for all x and d, p of x can be written as for all x and d, if x and d, then p of x. And then for some x and d, such that p of x can be written as for some x and d, and p of x. So the interesting thing is they added in this if x and d, then p of x for the universal quantifier, and we have the x and d and p of x for the existential quantifier.
Yeah.
I don't know. I don't see any reasoning for that. I kind of get the reasoning, but I didn't see it explicitly mentioned.
Yeah, I guess it's a matter of just conventions of the particular language. But I guess the statements on the right are equivalent to the ones on the left, because like for all x and d p of x, that means like for all x, if x is in d, then p of x. And there's there is an x and d such that p of x means, if that's the case, then there is something such that it's in d and p of x. So I guess they're equivalent, but I guess it's like a matter of convention which one you use.
What do you mean by which one you use?
Like
Like,
like whether you use the ones on the left or the ones on the ones on the right would be a matter of convention.
Interesting. Yeah. I mean, what wasn't explicitly made clear was why you'd have to use the conditional if when using the universal statement, universal quantifier.
Yeah, I guess you don't strictly have to in order to express the statements, but I guess it's maybe just some particular languages just happen to not have just happen to work that way where there isn't a way just to say like for all x and then specify that all the x's are in D. So you have to like instead say for all, you can only say for all x, and then like to capture the D part, you would just say like if x is in D and like treat that kind of like a predicate.
Yeah, it's pretty interesting. I think you mentioned it before. I guess if you just say for all x, it doesn't capture the fact that you mean for all x within a certain domain.
Yeah.
But then with the existential quantifier, um, I guess you don't have to use a conditional statement with it.
Yeah. Yeah, I guess that's it. Like there exists an x in D such that P of x. That's the same thing as saying there exists an x such that it's in D and P of x.
Yeah.
And I guess like maybe like some computer languages like don't have the word such that and
Right.
it might be like kind of, yeah, maybe the language wouldn't work well if you like had to insert the word such that. It's like much more compact to just have like there exists an x such that there exists an x and then have parentheses x and D and P of x.
Let's see. We illustrate the use of these facts in example 3.3.1. Consider once more the Tarski oil to figure 3.3.1. Let triangle x circle x and square x mean x is a triangle, x is a square, or x is a circle and x is a square. Let blue x, gray x, and black x mean x is blue, x is gray, and x is black. Let right of x and y above xy and same color as xy mean X is to the right of Y, X is above Y, and X has the same color as Y. Use notation X equals Y to denote the predicate X is equal to Y. Let the common domain D of all variables be the set of all the objects in the Tarski world. Use formal logical notation to write each of the following statements and write a formal negation for each statement. Okie doke. Let's see here. So for all circles X, X is above F. I think this would be for all circles. So for all X, if X is a circle,
Yeah. And then they made that into a predicate circle of X, set of X and C. Yeah.
then X is above F. And the negation would then be there exists an X such that, and I know the negation of a if statement is whenever the hypothesis is true and the conclusion is false.
Yeah.
Okay. And then
Yeah.
the next one. For all
For all,
circles.
yeah, so that one's almost it, but like, so like you said, the hypothesis is true and the conclusion is false. So we'll have circle of X and not above X. So instead of an if then, we'll have an and. And in fact, you would get the same result if you had like for all X and C above XF, because then you would have there exists an X and C such that not above XF, which would be equivalent to there exists an X such that circle of X and not above XF.
Say that one more time.
So like you would have gotten the same result if you used the earlier convention, like if you had instead if it had instead been for all X and C, X is above F. Because then in that case, to get the negation, you would say there exists an X in C such that not above XF. And there exists an X in C such that not above XF. That's the formal way of writing that. It would be there exists an X such that X is in C or circle of X and not above XF.
I see. Now let's see here. What relationship does the in an if statement when the hypothesis is true and the conclusion is false, what relationship does that case have with the case when the hypothesis is true and the conclusion is true?
I guess there isn't necessarily a relation. It's just like if the hypothesis is true and the conclusion is true, the whole thing is true. But like the key thing is like what you said, that like the hypothesis is false and the conclusion is, or sorry, the hypothesis is true and the conclusion is true. Or sorry, no, the hypothesis is true and the conclusion is false. That's the one case where the whole conditional is false. So that, like you said, the negation of the conditional is like saying hypothesis and not conclusion.
Interesting. Okay. But so they don't have opposite truth values.
Wait. Well, I guess. Well, if the hypothesis is true and the conclusion is false, the whole thing is false. If the hypothesis is true and the conclusion is true, the whole thing is true. So I guess in those scenarios, like those particular truth values for the component parts, you do get opposite truth values for the whole conditional.
Hmm. Oh, I think I'm getting it. So, like, if X then Y is not the opposite of if X then not Y.
Yeah,
Because there's a
yeah,
case in which they have the same truth value.
yeah, yeah, exactly.
And that case is when X is false, right? Those cases, when X is false, they would have the same truth value.
Yeah, yeah, exactly.
But in this case, if X then Y is the exact opposite, or it's the negation of X
Uh,
and Y. No, X and
yeah,
not
or
Y.
yeah, yeah, exactly. Yeah,
Huh. Well, let's see what the next one is. So, there is a square X such that X is black. Well, that's written as for some, there exists an X such that X is a square and X is black. Hmm. The negation is for all X. For all X, it's not the case that X is a square and X is black. And then you can use the Morgan's law to make it X is not a square or X is not black.
yeah,
Or let's see here. For all circles X, there is a square Y such that X and Y have the same color. So that's written as for all X, if X is a circle, then there exists a square Y and that Y has the same color. So it says for all circles X, there exists a square such that X and Y have the same color. So let's see, for all X, if X is a circle and there exists a square of the same color,
yeah, yeah. So they have like same color as X, Y.
okay. Hmm. I
Yeah,
think
and
that
then
you, hmm.
oh, go ahead.
I think that you'd probably be pretty good at coding. because like I see two ways to come at programming. There's one which is like playing with Legos, you just kind of trial and error your way through. And then two, you would do all of this logic before you even touch the code to begin with. Whatever program you're trying to build, you basically calculate all the logic and like design the code. And
Yeah,
then figuring out the syntax is like kind of like child's play, a bunch of Googling or whatever. But it seems like the depth of your knowledge would be in that first step of like designing the logic, the logical framework of the application. Seems
yeah,
like that's what your specialty is.
yeah. Yeah, oh, thank you. Yeah, I mean, I really like logic. And yeah, it's nice. Yeah, computer science, like, yeah, it's useful to kind of like be able to like logically formulate, like what do you want the program to do? And then
Mm-hmm.
yeah,
And precision is pretty important to the quality of every program.
yeah,
So let's see. The opposite. For some x,
yeah. And then we're negating a conditional.
right, we would say that the hypothesis is true and the conclusion is false. So for some
Yeah,
x, x is a circle, and now the conclusion is false. So we would negate the conclusion, which happens to be an existential quantifier.
yeah,
So negate that would turn it into a universal quantifier, and its scope would be negated. So the negation of this and statement is negating each of the components and changing the and to an or statement. So for all y, either y is not a square or y does not have the same color as x. Last but not least, there exists a square x such that for all integers or for all triangles, x is to the right of y. Okay, so there exists a square x such that for all triangles y, x is to the right. Okay, there exists a square x. There exists an x such that x is a square, or such that. Okay.
yeah. X is a square.
And
Uh,
for all
yeah,
triangles, y, x is to the right. So for all y, if y is a triangle, then x is to the right of y. The opposite would be for all x, either x is not a square or for some y, for some triangle, Alright, for some y is a triangle. By the way, can you still hear the music, or is it too low to hear?
Let me see. Can you still hear the music? Oh yeah, I can hear it in the background.
Okay, nice. Now let's see. There exists a y such that y is a triangle, and it's not the case that x is to the right of y. Now let's see.
Yeah. Yeah, great. You're combining a lot of logical rules at once.
Right. So let's see here. Oh, we're supposed to do something else?
No, just
That's
that.
it. Okay. So the statement looks good. And the negation looks good. We have C is this one. Okay.
Yeah. Yeah, so definitely in good shape with regard to the logical skills.
Indeed.
Yeah.
Was that a pun?
Yeah. Yeah, pun intended there.
Hilarious.
Right.
So let's see. The disadvantage of the fully formal notation is that because it is complex and somewhat remote from intuitive understanding, when we use it, we may make errors that go unrecognized. The advantage, however, is that operations such as taking negations can be made completely mechanical and programmed on a computer. Also, when we become comfortable with formal manipulations, we can use them to check our intuition, and then we can use our intuition to check our formal manipulations. Formal logical notation is used in branches of computer science such as artificial intelligence, program verification, and automata theory in formal languages. Taken together, the symbols for quantifiers, variables, predicates, and logical connectives make up what is known as the language of first order logic. Even though this language is simpler in many respects than the language we use every day, learning it requires the same kind of practice needed to acquire any foreign language.
Yeah.
You want this section?
Yeah. So the programming language Prolog, short for Programming in Logic, was developed in France in the 1970s by A. Kolmarauer and P. Roussel to help programmers working in the field of artificial intelligence. A simple Prolog program consists of a series of statements describing some situation, together with questions about the situation. Built into the language are search and inference techniques needed to answer the questions by deriving the answers from the given statements. This frees the programmer from the necessity of having to write separate programs to answer each type of question. Example 3.3.11 gives a very simple example of a prologue program. Consider the following picture, which shows colored blocks stacked on a table.
Okie doke.
And it's kind of ironic, by the way, that the prologue is coming at the end. Normally you get the prologue at the beginning.
Hilarious, true.
Yeah. Let's see. So the following are statements in prologue that describe the picture and ask two questions about it. So we have like predicates, is above G B1, meaning G is above B1, is above B1, W1 is above W2, B2 is above B2, B3. And then question mark, color B1 blue, color G gray. So I guess we have like more predicates, like color G gray means the color of G is gray. And similarly, color B1 blue, color B2 blue, color B3 blue, color W1 white, color W2 white. And then we have an is above predicate, is above XC, so X is above Z, if is above XY, and is above YZ. So X is above Z if X is above Y, and Y is above Z. And then we have question mark is above XW1. So maybe I guess they'll explain the question mark part. The statements is above GB1 and color G gray are to be interpreted as G is above B1 and G is colored gray. The statement is above XZ if is above XY and is above YZ is to be interpreted as for all X, Y, and Z, if X is above Y and Y is above Z, then X is above Z. So here they're kind of taking the universal quantifiers as implicit in this language. If you kind of just like use variables without context, it's assumed that you mean like for all variables, for all X, for all Y, for all Z. The program statements question mark color B1 blue is a question asking whether block B1 is colored blue. Prologue answers this by writing yes. The statement question mark is above XW1 is the question asking for which blocks X, the predicate X is above W1 is true. So they use instead of a constant, like B1 was a constant representing a particular block, X is a variable. So if you put a variable in the question, you're asking like for all the possible values of the variable that would make that true. So prologue answers by giving a list of all such blocks. In this case, the answer is X equals B1, X equals G. Note that prologue can find the solution X equals B1 by merely searching the original set of given facts. However, prologue must infer the solution X equals G from the following statements: is above GB1, is above B1 W1, is above XC if is above XY and is above YZ. So it's yeah. So like if G is above B1 and B1 is above W1, then G is above W1. Plugging in the specific constant values for the variables in the third statement. So write the answers prologue would give if the following questions were asked to the program above. Question is above B2 W1.
Let's see. B2 above W1. Well, B2 is here. Huh. So I wonder how it would be able to tell if B2 is above or not above B1.
Yeah. Uh, let's see. We can try using that rule. Like if x is above y and y is above z, then x is above z. I guess we can use that rule to like order everything, like or as much as we can. Like we know that G is above B1 and B1 is above W1. So we have G on top, or so far we got G on top, and then we got B1 below it. Then we have W1 below that. And
But it seems like G,
yeah,
B1, and W1 don't have any links to W2, B2, and B3.
yeah. Oh yeah. So I guess in that case, maybe the computers wouldn't be able to respond. It's like maybe we'll return an error.
Yeah, it depends on what it does. Because it could either interpret this as B2 is not above W1, like it be false by default, or it could conclude that there's not enough information to know for sure.
Yeah. Yeah, I would guess it would say the latter, like that there isn't enough information.
Let's see. Color. Um, what color is W1? Well, they could just look it up. W1 is white. And then color X in blue. So what objects are blue? You could also look that up. B3, B1, and B2. Let's see what it says. So it says that the question is B2 above W1. The answer is no.
It's B2. So you're right then. That assumes no by default.
Hmm.
Interesting.
And the rest were simple enough. Test yourself. To establish the truth of a statement to the form for all x in D, there exists a y in E such that P of xy. You imagine that someone has given you an element x from D, but that you have no control over what that element is. Then you need to find blank with property that the x the person gave you together with the blank you subsequently found satisfy blank. So you would need to find a y in E. You need to find the y in E with the property that the x the person gave you together with the y in E you subsequently found satisfy P of xy.
Uh, uh, oh yeah.
Let's
Well,
see. Hmm.
yeah, the wording is kind of confusing. Imagine someone's giving you some arbitrary x and d. And you, uh,
Because it doesn't matter what x they're given, since for all x in D, this scope holds true.
yeah, yeah. I don't know why they say you have to find y and e, or you have to find something twice.
Oh, I
But
think
yeah, maybe we can talk about the answer.
I think you only have to find it once. It just shows up twice in their sentence. So if I read it without the NE, it'd be a little clearer. Like, you need to find y with the property that x the person gave you together with the y satisfies p of x.
Oh yeah. Oh okay. Yeah, got it. Uh,
Mhm.
yeah, I think I was confused because I thought it was like saying like you need to find a y and e that has the x property or something. But
Oh, yeah.
yeah.
Let's see. To establish the truth of a statement of the form, there exists an x and d such that for all y and e, p of x, you need to find an x so that no matter what y a person might subsequently give you, p of x will be true.
Yeah. Yeah, an x and d and then a y and e.
Yes.
Yeah.
Consider the statement for all x, there exists a y such that p of x, a property involving x and y, is true. A negation for the statement is, I think it's, there exists an x such that for all y, p of x y is not true. It's not the case that p of x y.
Yeah.
Exists an x such that for all y, not the case that p of x. Consider the statement, there exists an x such that for all y, p of x y, a property involving x and y is true. The negation of this statement is, for all x, there exists some y such that p of x is not true. I wonder how the such that is affected by the negation.
Mhm.
So if I wanted
All
to,
right.
hmm,
Oh, oh, go ahead.
if I wanted to preserve the words there rather than removing them, it would be
Yeah, yeah. I guess you can't. I guess it's not possible to keep them there just by the convention of how people say these things. But
right.
I think getting the such that doesn't really have that much meaning. It pretty much just like intro says like now I'm going to give you the scope of the quantifier. It's
Right.
kind of just like it just introduces the scope, and it kind of just happens that by convention people use it with their exist, but not with for all.
Ah, I guess he just put the such that after the exists, there exists a y.
Yeah.
For all x, there exists a y such that instead of a comma, you could do that.
Oh yeah. Yeah. You could.
Suppose p of xy is some property involving x and y, and suppose the statement for all x and d, there exists a y in E such that p of xy is true. Then the statement for some x in D such that for all y in E, p of x is true or is false or may be true or may be false. So let's see here. For all x in D, there exists a y in E such that p of xy. And then over here we have for some x in D, for all y in E, p of xy.
Yeah. So you think about like personally, what's the difference between those two statements and their form?
Let's see. I wonder if there's any higher level intelligence way for me to describe the difference. I know just like the simple way of describing it is by just reiterating what they mean in clear terms. So, like in the first one, for all x and d, means like for every object in that set D, there exists a y and e that's paired with it through p of xy. Whereas, so every x and d is paired with at least one thing in y. Whereas the other statement is saying that at least one x in D is paired with everything in Y.
Yeah. Yeah, exactly. So they're saying different things, and like and in terms of their form, like the quantifiers are reversed.
Right. And then in terms of the logical equivalence, well, we know that they're not logically equivalent, but as we like talked about before, they're not contradictory either.
Yeah. Yeah, so given that the first one is true, like what could we conclude about the second one?
It might be true.
Yeah, it might be true, it might also be false. Yeah. Yeah,
Nice.
like in the example you found earlier, like like with the world where there's just one square and one triangle, and P of X, Y is they have different colors.
Exactly.
Yeah,
Now, finally, that was
yeah,
it seemed like a long chapter.
yeah,
I don't even
yeah.
know
I think
if it's, yeah, it's a
there's
long chapter.
one more section in the chapter, I think.
Really?
Yeah. Yeah, and then it gets to proofs finally in chapter 4.
Let's see. So that next one goes from 132. What's this? Proving validity. On what page does this last one end?
Let's see.
Oh, it ends on 144.
Oh, okay, so it's less than 10 pages.
Nice, nice. Well, I think that will conclude our lesson for today.
Yeah. Yeah, that'll be interesting next time to look at like making arguments with first order logic.
Arguments. That does sound interesting.
Yeah.
Let's see. All right. In that case, I'll be ending this stream.
Okay. Yeah, that was fun. And yeah, thank you to anyone watching.